Today we're going to look at transformations, how we move shapes around the coordinate plane, and some symmetry things. So transformations are a mapping or a movement of an object. There's really nothing to add to this definition, but we see on this graph that we either started at PRQ and we moved it to MON, or maybe we started at MON and we moved to PRQ. That's what a transformation that we're going to look at in this class, moving things around. All right, so we always have our pre-image and our image. Our pre-image is the original figure, and it has specific notation, capital letters. Okay, capital letters, kind of like we did with points back in Unit 1, just a capital letter. The image is what happens after we make the transformation, and it has its own notation. So it's, for example, A with an apostrophe, and how we read this is A prime. So if we look at the diagram next to our definitions of pre-image and image, we see our pre-image is A, and our A prime is our image. It's the second one. It's after we performed a transformation to it. Now there's three different transformations that we're going to look at. A translation, which we also call a slide, because that's the action that it does. Okay? Excuse me. So if we look at this drawing, this graph, we start here at the black image, and I know that because it's just TSU. We slid it up to T prime, S prime, U prime. So that's how I know it was a slide, because everything remained in the same order, and it just shifted up, down. Well, in this case, up. All right. Our rotation is called a turn. It turns around a fixed point called the center of rotation. And a lot of times what we do, at least at the beginning when we look at rotations, is we use the origin. Now, if you look at figure 1 versus figure 2, again, I know that figure 1, TUVS, is where we started because it doesn't have those apostrophes. It doesn't have that prime notation. When I look at T prime, U prime, V prime, S prime, you notice I'm calling them all primes. The order is different, okay? We turned it. We rotated that shape. The last one we have is a reflection. We also call it a flip. It's flipped over a line of symmetry. In this case, we used the y-axis as our line of symmetry, but we can use the x-axis and any number of things for our line where we perform the flip or the reflection. My apologies. Again, I started here at FGHI, flipped it over the y-axis, and I have F prime, G prime, H prime, I prime. Excuse me. All right, we're going to name the type of transformation in the picture below. All right, notice it's given us a hint. It is said that the pre-image, where we started, is the dashed figure. So since we don't have any letters showing us A, B, C, A prime, B prime, C prime, I'm going to go ahead and I am going to number everything. Because that way I have a better comparison and I can say, okay, how did I get from shape 1 to shape 2? So first, let's look at A. Going from shape 1 to shape 2, the direction stayed the same. It doesn't look like it flipped over left or right or turned around. Okay, this is a slide, also known as a translation. Now, we have called translation a slide, but when you're doing your work, we really do need to call it its proper geometric term, which is a translation. All right, let's look at B, going from figure 1 to figure 2. All right, so we went across the y-axis, but if you notice, the long side changed. Okay, instead of being upright, now it's laying flat. So I want to look at my physical features to determine what kind of transformation that I have. And in this case, I see that I have a rotation. All right, now let's look at C, going from 1 to 2. What I tell my students is that reflections are kind of like looking in the mirror. They're almost backwards. So if I took image 1 and I flipped it over, I would get image 2. That's how the reflection works. But you see that things are opposite. The flat sides are facing each other. The pointed sides are facing out. That's one indication that we have a reflection. Okay, this is a reflection on the y-axis. Now, if we look at D, going from the dashed or figure 1 to the solid figure 2, we have another reflection, right? Because those flat longest sides are facing each other, and the tip that's facing downward on shape 1 is on the top for shape 2. This is again a reflection, but this time it's on the x-axis. We will get into this more when we look at reflection specifically, but starting out, being able to identify those things is helpful. All right, now we are going to look at symmetry. So we have some definitions. When two figures are identical after a transformation, we say that they are symmetrical, that symmetry has happened. If a figure can be symmetric after a reflection over a line, we know that we have a line of symmetry. Okay, so translations are not going to be symmetrical because there's not a line of symmetry, nor is there a rotational point. So symmetry is really reserved for reflections and rotations. So as far as rotational symmetry goes, if a figure can be symmetric after a rotation of 180 degrees or less, that's what we call rotational symmetry. The figure must repeat its pattern as it turns. All right, so what we're going to do is we're going to look to see if we have line symmetry or rotational symmetry, okay? And we're going to guess the number of degrees. And the reason that we're keeping it to 180, which is half a circle, is because after 180 degrees, we typically see 360, which puts the shape back to where it originally began. So everything has that kind of rotational symmetry. So we're going to look at 180 degrees or less. All right, we are going to first decide if line symmetry is in place on our figures, and we're going to state the number of lines, if possible. Then we're going to look to see if it has rotational symmetry and the number of degrees. So sometimes you can have both. It just depends on what kind of symmetry you're looking for. All right, so with my line symmetry, what I want to do is I want to try to see if I can find lines that I can flip the shape on top of itself, and it's going to be the same thing. So as you see, I found 3 ways where I can fold this shape in half, and it's symmetrical. Okay, they're identical. A reflection happened, and it's line symmetry because it's symmetric. Now, also, we have rotational symmetry, because if you notice, our lines of symmetry broke this up into 6 even portions, okay? Now, if you recall, a circle is 360 degrees. So if we were to determine that we have rotational symmetry, what we want to do is take 360 and divide it by how many pieces are identical. So in this case, we're going to take 360 and we're going to divide it by 6 even pieces. And so we have 60 degrees for rotational symmetry. All right, let's look at number 2. If we look carefully, I can find one line of symmetry. Okay, I can't find it the other way because when I fold it in half, it doesn't necessarily ensure that things fold onto itself exactly. We also have rotational symmetry because if I take this portion, I can rotate it here one time. So I have 2 even sections, and that gives me rotational symmetry. And it's rotational symmetry of 180 degrees. All right, let's look at number 3. Do we have line symmetry? Well, at first you might think, well, no, there's a big chunk missing. But look where I drew this line. Okay, we have even empty space here if I fold it on top of itself. So yes, and we have 1. But on this one, it's not rotational because with a figure that looks incomplete like this, there's not a way to break it into sections that could move those number of degrees and keep the same form. Last one. Let's look at number 4. First, we want to see if there's line symmetry. And these wheel shapes with the spokes, they're really, really helpful, okay? It gives us some clue that, hey, we have some line symmetry. So just like our number 2, we want to follow the given lines. All right, so yes, we have line symmetry. We have 4 of them. And just like with number 2, if you notice, it's broken up into all these equal pieces. Like if I were to divide this apart, it would be the same thing. So we have 8 sections. So we're going to take 360 divided by 8, and we're going to get rotational symmetry of 45 degrees. All right, thanks for watching. And if you have any questions, be sure to ask your math teacher. Have a great day.